Welcome to my channel, Arun Kumar at Exam Guru. This video is related to environmental engineering, a topic of civil engineering. There will be 5 multiple choice questions on water demand. First, let's look at the components of a water supply system. There will be an intake structure near to the river which carries the river water and transfers it to water treatment plant by means of a pump. And from the water treatment plant, the water is transferred through conduits to water tank or reservoir, and from that it is transferred to the individual households by means of distribution mains. The components of water supply systems are intake structures, pumps, water treatment plant, water tank or reservoir, and distribution mains. What are the factors that affect the water demand in general? There are 3 factors. Number 1, rate of demand. Number 2, design period of the components of the water supply scheme, and the population. Number 1, rate of demand. So it represents the average consumption of water per person per day. If V is the total quantity of water in liters per year for a town having a population P, then we can calculate the average rate of demand Q equals V divided by 365 into P liters per capita per day. In the denominator, there is 365, which denotes the number of days per year. And number 2, the factor is design period of the water supply scheme. So it's the duration for which a water supply project is planned to meet the future water demands. The design period should neither be too long nor too short, and the design period of a water supply project is taken as 20 to 30 years. What are the factors considered in the design period? Number 1, useful life of component structures. The design period should not exceed the useful life of components. So the components which are already discussed, which include the intake structures, followed by pumps, followed by water treatment plants, followed by water reservoir and distribution mains. Difficulty in future expansion. If future expansion involves a lot of difficulties, longer design period should be chosen. Availability of fund. If there are limited funds, then shorter design period is selected. And the rate of population growth. If there are less rate of increase of population, longer design period is adopted, because if there is more population growth, the people may shift from that place, and longer design period in such case may be unnecessary. What are the design period of structures? For dams and reservoir tanks, it is 30 or 50 years. For conveying pipes or distribution system, it is 30 years. For filtration works, it is 30 years. In the case of pumping works for the pump inside the pump house, it is 30 years, and for electric motors or electric pumps, it is 15 years. For water treatment units, it's 15 years. For the reservoir at the headworks, it is 15 years. What are the different types of water demand? Number 1, domestic water demand, which constitutes 50 to 60% of the total water supply. 20 to 25% goes to industries, 10% goes to institution and commercial purpose, 5% goes to public or civic use, and 5 to 10% for fire demand. So number 1, domestic water demand for large city and town. For full flushing system, it is 200 liters per capita per day, and for small city and town, for full flushing system, it is 135 liters per capita per day. For industrial water demand, for large city and town, it is 450, and for small city and town, it is 50. And number 3, institution and commercial water demand, that is water required for hospital, schools, railway station, office, etc. The water demand is 20 liters per capita per day, and for public use, it is 10 liters per capita per day. And the last category, that is the water required for fire demand, that is to extinguish the fire. There are 4 different formulas. So number 1, Buston's formula, where Q equals 5663 root P. So in all the 4 formulas, Q will be in liters per second and P will be in thousands. So the water is used to extinguish the fire from the fire extinguisher. The second formula will be Pichling's formula, where Q equals 3182 root P. Third formula is Freeman's formula, which is given as Q equals 1136 P by 5 plus 10. And the fourth formula is National Board of Fire Writers formula, where Q equals 4637 root P 1 minus 0.01 root P, and fire is extinguished by water. So in all these four formulas, Q will be in liters per second and P will be in thousands. Now let's look at a typical graph showing the hourly variation in demand of water. So on the x-axis, it shows the time of a day, and on the y-axis, it shows the quantity of water in million liters. So if you look at the graph, the straight line represents the actual demand and the dotted line represents the average demand, which is Q, and the formula of Q is previously discussed. So if you look at the actual demand in the morning from 12 to 5 a.m., there will be very low demand, and from 5 to 10 a.m., just after waking, the water demand will be very high. So there will be an increase in the water demand. Then after 10 a.m. to 3 p.m., the people will be at the office, so the requirement of water will be reduced and there will be a decline. Then after 3 p.m., when everyone reaches the house, the demand starts increasing. So this is a typical diagram showing the variation of actual demand, but the average demand remains a straight line because average demand is calculated by the formula which we have discussed before, that is V by 365 into P. Now how can we assess the maximum demand of water? The maximum daily, hourly, weekly and monthly variation can be calculated by the following formula of R.O. Goodrich. The formula is P equals 180 T raised to minus 0.1, where P is the maximum demand by annual average demand and T is in days. So if you consider daily, in the case of daily, the P will be maximum daily demand by annual average daily demand. If it is hourly, P will be maximum hourly demand by annual average hourly demand. Now let's take the maximum daily variation. If Q is annual average demand in liters per capita per day, then using Goodrich formula, substitute T as 1. In the formula, we get P is 180%. Hence, P will be maximum daily demand by annual average daily demand, which is 180%, that is 1.8. Hence, maximum daily demand equals 1.8 times the annual average daily demand. Number 2, maximum hourly variation. Using Goodrich formula, substitute T as 1 hour, that is 1 by 24 in the equation, we get the value of P as 270%, that is maximum hourly demand by annual average hourly demand is 270%, that is 2.7. Hence, maximum hourly demand is 2.7 times the annual average hourly demand. And there is one more relation. Maximum hourly demand is 1.5 times the average hourly consumption of maximum daily demand. Now, if you look at the maximum weekly and monthly variation, using Goodrich formula, substitute T as 7 days for weekly and 28 days for monthly, we get P as 148% for T equals 7 days and P as 128% for T equal to 28 days. Hence, maximum weekly demand is 1.48 times the annual average weekly demand, and maximum monthly demand as 1.28 times the annual average monthly demand. Now, there is a term which is known as coincident draft. So, coincident draft is the maximum of maximum daily demand plus fire demand or maximum hourly demand. The capacity of different components of a water supply scheme. For intake structure, it is capacity is maximum daily demand, and for the conduits to reservoir, it is maximum daily demand. For water treatment plant, it is twice the annual average water demand, and for pump, it is twice the annual average water demand, and for distribution mains, it is coincident draft. What are the factors affecting the annual average water demand, that is Q? So number 1, size of city. Number 2, system of supply. Number 3, climatic conditions. Number 4, habits of people. Number 5, pressure in the distribution system. Number 6, efficiency of water works. Number 7, sewerage facilities. Number 8, water charging methods such as metering. So number 1, size of the city. For large cities, there will be more water consumption, and for small cities, it will be reverse. And for system of supply, if there is continuous system of supply, you can see there will be more wastage of water. And if there is intermittent supply of water, there will be less wastage of water. Number 3, climatic conditions. And for hot climate and cold climate, you can see the difference. For hot climate, more water is necessary. Then habits of people. So one on the left shows the people with more economy, where there will be more usage and wastage of water. The number 5, pressure in the distribution system. So if the pressure is larger, there will be more flow of water, and if the pressure is lesser, there will be less flow of water. The efficiency of water works. If you look at the figure on the left, the efficiency is very less, so inefficient water system may even lead to epidemics. But the figure on the right, the water works are very efficient, so people are happily drinking the water. Then sewerage facilities. One on the left shows a cities with proper sewers. So in order to clean the sewers, more waters are necessary. So cities with proper sewerage system require more water. And one on the right shows villages where there are no sewers, so less water is necessary. Then water charging methods such as metering. So the figure shows a water meter. If there is a presence of water meter, then the owner of the house will think, should I use more water? That means use of meters will lead to less water consumption. Now let's look at the questions. Question 1. The water supply scheme is designed on a town having a population of 1 lakh and has an average water consumption of 250 liters per capita per day. The maximum daily demand of the town is. So let's first calculate annual average demand Q. How we calculate that? So we calculate it as 250 liters per capita per day, that is the average water consumption by the total population, which comes out to be 225 into 10 raised to 6 liters per day, LPD, that is 25 million liters day, MLD. Now what is the question is to find maximum daily demand. We have already discussed maximum daily demand is 1.8 times the annual average daily demand. So 1.8 into 25 will get the answer as 45 mld. Hence the right answer to the question is option C, 45 mld. The next question is the design period of distribution system is, it was already discussed. The right answer will be option A, 30 years. Question 3, the industrial demand for large cities and town is. The right answer is option B, 450 liters per capita per day. Question 4, the Kiechling's formula for water demand is. So it's a fire demand formula. The right answer is option D, 3182 feet. And question 5, the distribution means are designed for. The right answer is option B, coincident draft. So thank you, and don't forget to like, share, and subscribe, and press the bell icon to receive more updates.